Hello and welcome to another video on the topic of statistics at just an introduction level. Now, hopefully you have watched some of my other videos or have a basic understanding of hypothesis testing and t-tests and all those things already. With this video, I just want to chat a little bit about confidence intervals, because I found that we might not understand where they come from and really how to view them. And on a basic level, this could perhaps help some. So let's look at a sample here. Let's make it 10. I'm just going to make up some numbers, right? And in our hypothesis test, let's suppose we're testing if the mean is, I don't know, let's make it 14 versus the alternative, oopsie, no, get rid of that, that the mean is not 14. So we have a two-tailed test. And let's suppose, first of all, we have, let's suppose here in case A, we get a sample mean of, let's make it 16. We approximate the standard deviation. I'm going to skip all of the distribution of the means. We have an approximation for our standard deviation of the appropriate comparison distribution. Let's keep it simple and make it a 1. Just so we can do many of these calculations in our head. So let's visualize the distribution. And let's do it over here. Distribution. Here is my attempt at some sort of bell curve. That's not bad, actually. So what is the logic mainly around the hypothesis testing procedure? Well, first of all, here we assume that our null hypothesis is true and the distribution is centered here at 14. Then we have a two-tailed test. We're going to pick an alpha, let's say 5%, sort of a classic, and we're going to split this up into two pieces, of course. We have 2.5% on either side, 2.5% on either side, and so we need our t cutoff score that we can look up in a table fairly easily. What did I say? Sample size of 10. So degrees of freedom is 9. We have a two-tailed test. Follow the 9. 2.262. 2.262 positive and negative, of course. Oopsie. 2.262. Those are our cutoff scores, positive and negative. And then we will calculate our observed t-score as our sample mean minus the null hypothesis mean over the standard deviation of the appropriate comparison distribution. Okay, so we're skipping some stuff here because our main focus, I want it to be on confidence intervals, but confidence intervals are very closely connected to the hypothesis testing reasoning. So I do want to see them both sort of together. Now we have a very simple calculation that I set up on purpose. And so we get an observed score of 2. Now, these are all just standardized versions of the 14 and the 16, of course. So let's color it a different color here and see, okay, right there, boom. that is our sample mean, or t observed. The sample mean leads me to the observed t-score, a nice convenient 2. All right. And then we can say that because of the positioning of this observed t-score in relation to the cutoff scores being more extreme, the sample doesn't give me an extreme enough observation. And our conclusion will then be to do not reject the null hypothesis. The evidence isn't strong enough to suggest that the distribution isn't centered at 14. May very well be. Okay, so let's now look on the way to a confidence interval. Let's now just look at this in a way that essentially takes this section, this interval, on my comparison distribution and just converts that to the corresponding raw scores. That's essentially what we're going to do next. So we're going to say under the null hypothesis, that is really the assumption we make to then use this distribution. It's under the assumption that the mean is at 14 or is 14. We can say that let's say it like this, under the null hypothesis, I'm going to not reject if my observed t-score sits between, whether we make that an equal or not, it's debatable, doesn't really matter for this discussion, sits between the negative t cutoff score and the positive t cutoff score that I'll just write like that. If I get an observed, like the pink one here, that sits in between here, then I'm not going to reject it. Okay? So now I'm just going to work with this and simplify this a little bit, but in general, I don't want to use the specific numbers. So the observed t-score is calculated as we did previously, and that is now going to sit between my t cutoff positive and negative, like so. Now just a little bit of algebra. I'm going to multiply both sides by this denominator throughout. I really do have two inequalities here, but we can sort of treat them as one in terms of simplification. And so I'll multiply throughout by this. So I'll get negative, let's say t, I'm just going to write t cutoff like that, times standard deviation, less than the numerator I still have left, t cutoff times standard deviation. Then I'm going to add both sides. I'm going to add the mu, the hypothesized, not population mean, distribution mean, through everywhere, and then I'll get mu plus the t cutoff score times standard deviation less than sample mean less than mu. I write the mu first, it just looks a little nicer. T cutoff times standard deviation. So these are all the same. These are all equivalent statements, equivalent inequalities. So what does that say? Let me zoom out a touch. We can see the picture as well. That's maybe too much zooming. An appropriate amount of zooming. Yes, maybe. So now, under the null hypothesis, 95% of the sample means I can get will fall between these two values. And these correspond to the left side of this interval I highlighted here and the right side of this interval I highlighted here. We've simply just converted the standardized scores or values to the raw scores in the unit of the original variable. So we haven't really done anything. But based on the familiar picture, simply a conversion, let's actually do it to see. We have a mean of 14 under the null hypothesis. So this will be 14 plus 2.262 times, I think I said 1 for simplicity. The left side, 14 plus 2.262 times 1. Just so everyone is completely convinced, we'll use a little calculator. We have 14, oh, both plus? No. I missed my plus. My minus accidentally turned into a plus here. That is not right at all. It was a minus there. Minus. Sorry for the confusion there. Let us see. 14. I know I can do it in my head, but, you know, for dramatic effect. 262. And I want to show my calculator. Times 1. Boom. 11,738. 11,738 less than the mean or sample means that I could get. Less than 16,262. So I can sort of see both. So under the null hypothesis, 98% of the sample means that I can get will fall between these, and these are just the raw scores that match the cutoffs. I then get a sample mean of 16, and I see, just like here, it falls in there. And so the hypothesis testing logic or reasoning is then to say, these two are the same, right? This interval on a standardized scale, this interval on the raw score scale, this is the exact same. But I want to get used to this rewriting to see how these are the same. And because my observed sample mean falls in this interval, I'm going to make the same conclusion. It is the hypothesis testing logic still to say that, well, I got something that sort of fits with this assumption. 95%, I could be anywhere in here. I can't really distinguish between them. It was only if I go a little bit more extreme, then I'll make a different conclusion. I'm well within what's possible under this assumption, so I will not reject the assumption. All right. So that's the hypothesis testing side. Essentially, in very broad terms, what we're doing is we're making an assumption about the population. Then we follow that assumption, see how our evidence sits in relation to that, and make a conclusion appropriately. Now let's look. Okay, so, I don't know why I made that A. It doesn't matter. Of course, if I got a sample of something else, then it would sit outside here, which would be sitting outside there because these intervals are different versions of the same thing. Now, let's look at the same situation, but from the confidence interval side. I'm essentially going to take this. I'm essentially going to take this, but I'm going to rewrite it in a different way by saying that, okay, well, I don't know if this comparison distribution is actually true. I don't want to make this assumption necessarily. Let's just rewrite this. Now, the algebra might bother some people, but it's still nothing insane. I'm going to not keep m in the middle. I'm going to keep mu in the middle. So I'm going to instead subtract m throughout, and I'll get negative m, just to really be clear on how it's really algebraically the same thing. I'm just thinking of this arrow. I'm going to crash into this arrow. Well, whatever. We'll cross that bridge when we come to it. So I'm subtracting m throughout. I need this arrow gone. I could make the cursor bigger, but that would ruin the fun. So let's go this way. Maybe that's enough space. And I'll get a negative m plus, so close, so close. Okay, so forget all of this. We're making a new interval. Well, technically not new, but a new way to look at it. Then I'm just going to multiply by -1 throughout, and I'll get a mu in the middle. All of these flip. The inequalities flip when you multiply by a negative number or divide, and I'll get m plus t cutoff times Sm and m minus t cutoff times Sm. Whether you fully are comfortable with that or not doesn't really matter. That's the algebra. And that is just what it is. So don't worry too much about this. What I'm now building is an interval around my sample mean. It's a little backwards, I suppose. This will be the lower one. You could flip it. The lower one will be on the left. You could flip it like that. Cutoff times Sm. But instead of making the assumption and essentially just converting the comparison distribution, we can say that, or we can interpret this as, I don't know where the true mean is. The best guess that we have is to center our distribution and to take the mean as the sample mean that we got. It's arguably a better guess. Then, based on that, 95% of, let's say here, let me just write something down, using m as our best guess for the center of the true distribution, 95% of sample means that we can get should arguably fall in this interval. With repeated sampling, we should get 95% of those samples in this interval. Let's actually calculate this interval. We had a sample mean of 16, right? 16 minus 2 points, no. What was it? Was it 626, 262, 262? Okay. 262 times 1. 16 plus 2.262 times 1. One more. Let's, for dramatic effect, use the calculator again. I so rarely use this application. I want to use it. 16 minus 2.262 times 1. 13. Oh no, it's gone. 738. 738. I know it looks very similar to the previous one, but we're technically taking a slightly different, looking at it from a different side, I guess is the best way to say it. This we're going to call the 95% confidence interval. Yes, it's a subtle difference between these two because really the conclusions that we make will be equivalent every time. But what we're saying now is let's build our interval around our best guess, which is the sample mean, and not just make some wild assumption which could be dramatically incorrect. Our sample is arguably our best shot. Then we build our interval around that sample mean and say and interpret that as, to the best of our knowledge and abilities, 95% of samples that we will get should be in this interval. We are guessing, of course. There's always going to be an element of guessing. It's the best we get. We can do an educated guess. We then can say, okay, let's see where the null hypothesis mean, which was 14, where that sits in relation to the confidence interval. And we see that, okay, it is inside the 95% confidence interval. And so our conclusion is that that was a perfectly possible mean that can actually be the true mean. We will never know. We can't narrow it down perfectly. The true mean can sit anywhere in here from sample means to a reasonable extent. 14 is in here. That could be it, and this evidence is not strong enough to suggest that it's not. So we can say the evidence is not strong enough to, let's say, reject this proposed true mean. And these conclusions will always match. The null hypothesis comes from making this assumption and following that string and seeing where the example, the evidence, sits in relation to that. The confidence interval arguably says, let's build our interval around the evidence. We have to spread our net a little bit. We can't take a single sample and say, oh, no, 16 is it. That's the true mean. It's over. No, there's randomness to all of these things. So we widen our net a little bit to a range that we decide beforehand, 95%, for example. Could make it 99, could make it something else. 95 is sort of the classic one. Because there's a chance we could be a little off. Then we see, okay, well, 95% of our samples will sit in here, to the best of our knowledge. 14 does fall in here, so it can be the true mean. We don't have evidence to suggest that it probably isn't. And so our conclusion is exactly the same. Now, of course, you can see here, well, let's maybe do something short here. If I took, let's go different color, let's go blue or something. Or purplish blue, I don't know what this is. If we change this to 20, clearly, very, very easily, because our numbers are convenient, in the hypothesis testing approach, our observation, our T observed, will be 6, way out there, way more extreme than the cutoff. We will reject the null hypothesis. If we take the confidence interval approach, we will build it around the 20, and we would get 17.738 to 22.262. And then we can see that the proposed true mean, 14, does not fall in this 95, oopsie, my writing is atrocious, 95% confidence interval. And our conclusion will again be that, well, 95% of our sample means should be in this interval. We are proposing that the true population mean sits way over here. The evidence does not support that. In fact, the evidence suggests that this proposed 14 is very likely to not be the true mean. We don't ever know what it is, but it's probably not 14. There's always a chance we could be wrong, but we're just trying to sort of hedge our bets and limit the chances of that conclusion being incorrect. So from the two-tailed test side, we hopefully now get a better idea of how the hypothesis testing argument roughly goes, confidence interval argument, how they are slightly different views to get to the same eventual conclusion.
Welcome to MathCats, where we aim to better understand mathematics. Join us weekly for discussions on elementary, high school, through to university math. You can request the next topic by leaving a comment on our YouTube channel or by emailing us at mathcats314@gmail.com. And as always, remember to like and subscribe. Thank you.
All right. So now I just want to, a little bit more briefly, mention the one-tailed situation to see what's the same and what's different. Let me just go up here and try and keep the example as similar as possible. The only difference now is that I'm going to have a one-tailed test and say, well, my null hypothesis is I'm testing if it's possible that the true mean is 14 versus let's go greater than 14. Let's visualize that. Now this is definitely the one that isn't as clearly discussed in books, perhaps because it doesn't come up that often. But it is worth noticing the little differences, a lot of similarities, but there are some differences, especially in the confidence interval. So we are going to, I just want to follow this as closely as possible here, make the same M16. Standard deviation of our comparison distribution is a 1. What else did we do? Not much. Now we will have our cutoff a little bit different so that all of this is 5%. What's our cutoff now? One-tailed, follow the 9, 5%, 1.833. So our T cutoff, 1.833. So in order to understand where the confidence interval, the confidence interval is going to look the way it does, I kind of have to do the whole thing again. If it bores you, well, that's completely up to you. I find it interesting. You can skip ahead. You can do whatever you want. But I want to be fairly thorough, at least in this one video, and not take unnecessary shortcuts. So first of all, the hypothesis testing approach is then going to calculate the same observed score, 16 minus 14 over 1, a 2. Let's make it, I'll go with blue, why not? Let's put it over there. Boop. And our observed t-score is 2 more extreme than the cutoff, and our conclusion will be to reject the null hypothesis. Reject the null hypothesis. Based on this, with 5% as our alpha, our probability of a type 1 error, or 95% confidence, it does seem that the true mean sits higher than 14. Just like you have done many examples like this by now. So now let's, a little faster, but still do the same thing. Because I want to not just slap the confidence interval formula on the screen. Any book can do that. Anyone can do that. Where does it come from? Why? How is it still the same? I want to see. So I'm going to take a very similar approach in that under the null hypothesis, I'm going to not reject the null hypothesis if thinking of my spacing, I'll put it over here. My t observed, actually no, I have only one side now, right? I don't have to balance this anymore. Let's go in here. T observed is necessarily greater, not reject, less than or equal, whatever, than the t cutoff. T observed has a formula m minus mu over sm. T cutoff, I can put it in. I'll do that later though. We're still just rewriting this, essentially this range, for lack of using a better word, I can use a better word, this interval all the way. That's my, I want to call it the safe zone if not rejecting is considered safe. And I'm just rewriting that to the raw score. Now this 14 I know is not actually 14. No, it isn't. This is standardized. So this will be t equal to 0, of course. But I want to write this to a raw score, which we can do, but I want to do it through an inequality. I'm going to multiply both sides by the denominator, t cutoff, and you're going to see a lot of similarity. Add the mu. I'll write it in front. And the t cutoff is only the positive side. So let's calculate this. Mu is 14 plus, what did we say, 1.833 times a very convenient 1. And we have 15.833 and just negative infinity. There's no cutting it off on the left. And then we can say, well, let me just see if this is exactly how I wrote it. Yeah, roughly. Okay. Then we can say, well, okay, under the null hypothesis, if the null hypothesis is true, 95% of my sample means will fall below 15.833, simply the raw score that corresponds to the cutoff. We then have a sample mean of 16, which is outside of this interval. And the hypothesis testing says, that doesn't seem to fit very well with our assumption. It's rare enough that we're going to see that as strong enough evidence to suggest, yeah, this is not the true mean. All right. So now again, for the confidence interval, we're going to take, let's take this one. And we're going to subtract m, same as what we did before, and just rewrite it like so, exactly the same. We just have one side now. Then we multiply throughout by -1, exactly what we did last time. Mu is then greater than m minus t cutoff times Sm. This will be, let's calculate this, will be, what's m? M was 16 minus, actually, let me just back up. This is a greater than, let's just flip it all around to sort of have it increasing from left to right, just like everything else that came before it. This will be 16 was our sample mean. 1.833 was our critical t-score, cutoff score, and 1 was the convenient standard deviation. And so that's for dramatic effect. I like to be dramatic here. Why not? 16 minus 1.833. And it also, using the calculator, slows us down a little bit and gives everyone a chance to just keep up with what we're doing. I forgot what the numbers were. 167. So now, let me just check if I did it the same way. Yes, we're over here. But now we have 14.167 on the left, and it is unbounded on the right. And this is our 95% confidence interval that corresponds to the one-sided situation that we had as our original question, really. And so we can now say that this is, from the confidence interval approach, it makes more sense to build our interval around the mean. We suspect that the mean is greater, but the true mean, but using our sample mean of 16, we need to again give ourselves a little bit of leeway, spread our net a little bit. Now we're only going to spread it to sort of in one direction, limit ourselves in one direction, that around the mean, no end on the high side, but limited on the left, because our mean is now, or our question is just sitting on one, is asking for one side only. And then we can say again, something to the, I don't want to look back every time, the words can change a little bit. Our mean of 14, our null hypothesis proposed mean that we're testing of 14 is not in this interval. Doesn't matter how close, it's not in. And so we can see that as, well, this is where 95% of the sample means should be. What are the chances that the true mean is outside of this? Very unlikely. Not impossible, nothing's impossible. But we can see that as strong enough evidence, to conclude that the true mean is in fact greater than, whoopsie, that's an ugly n, greater than 14. We don't know where. With 95% confidence, it's somewhere in here. But that wasn't really our question, right? Our question was, explore if it is 14 or if it's potentially greater than 14. So let's zoom out a little bit. So it is a little different and less common to look at a confidence interval that matches the one-tailed question, or the one-sided question. And by looking at the inequalities and using some algebra, hopefully now you are a little bit more comfortable and feel a little bit more convinced why the formula is necessarily, in the one-tailed case, one-sided to this side. And in the two-tailed case, zoom out. The two-tailed case, where the formula comes from. It's one thing to just blindly memorize a formula, but it doesn't give me as much value if I do that too often. We're totally capable of understanding the different viewpoints that the hypothesis testing approach and the confidence interval approach take, yet arriving at the same conclusion. All right, that was long enough, I think, but hopefully that helped some of you, and hopefully it clarified some issues regarding confidence intervals. Until next time.